Right, welcome viewers. Today we want to continue on what we did on prestress concrete design. In our last lecture, we treated prestress concrete non-composite section using the extreme fiber stress criteria. So today we want to continue on the derivation of the necessary equation for obtaining the prestressing force and also determination of the required cable zone for the prestressing force. Now, let's start by reminding us of what we did. In the last lecture, we were able to establish the necessary inequalities for obtaining the stresses at transfer and the stresses at the point of at the service life of the structure. This we did in our last previous lecture. Call it 2A, whatever you want to call it. Okay, so we have all this equation. Now this next equation we have is eccentricity. These are what we call the upper limit of the prestressing force. The upper limit of eccentricity we have Z1 over A in brackets, get minimum fiber stress minus N2 Z1 over P, and we have close bracket, we have M2 over P. Let's call this one equation 3A. Okay, so we've got an equation 1. The last one, we have 4 equations. The last one is this. We have it as our maximum fiber stress minus N2, we'll close bracket. We have Z2 over P, and we have minus Z2 over A, and close bracket, and we'll have minus M2 over P. Let's call this one equation 4A. All right, so what we've just done, we've rewritten those equations we got in our first video. So we're going to continue with these equations, okay? Now, what we want to do, if you look carefully, we want to establish a cable zone for our beam or our slab, whatever you are designing for. Now, for us to obtain this cable zone, the cable zone, like I told you, is the point, the zone within which the resultant prestress force must act in order for the section to meet up with the necessary criteria of prestressing limits. All right, so that is a cable zone. So, but if you look at it, because the cable zone we are talking about, if I may do a little illustration, let's assume we have a beam. Let's assume we have a beam of this nature. Let's assume these are neutral axis of our beam. We'll call it our neutral axis of the beam. Let me make it a little deeper. So let's assume these are beam, okay? And let's assume we have a neutral axis somewhere around here. Now, the cable zone is expected to take this format, all right? It's going to go like this. We'll have the cable zone coming like this, okay? So it's either it goes below the neutral axis or the zone goes above the neutral axis. So if we can say, okay, this is our cable zone, this is our cable zone, all right. We'll call this one our neutral axis, okay. So if this is a beam, for instance, a section of the longitudinal direction of a beam, of course, if we take a section of it, now we know definitely that the moment in the beam varies along the span. So for every section of the beam you take, you are expected to have a different value for your bending moment, both for bending moment due to dead load and also bending moment due to dead load plus live load. So you are going to be having, so you can see that in the initial case, for example, let's take a continuous beam. You have your bending moment go this way. You can see that for every section, your bending moment is changing. Uh, at this point, we're having it as positive bending moment. At this point, we're having a negative bending moment. So uh, we can look at the variation of the moment. So in a bridge design, you are going to see the same. The cable zone of this particular, let's assume is a continuous beam. You can see that the cable zone, the value for the cable zone will differ at each section along the span of the beam. And that is why you can see that the value for your M1 and M2 will varies along the beam. If it's a simply supported beam, it's a continuous beam, whichever you are designing for, the value of your M1 and M2 varies. Let's assume your M1 is your live load. Of course, even if you analyze it for self-weight, you discover that you still have your moments varies along the beam. So if you are designing a bridge, for instance, you first of all need to obtain the moment at different sections. I think we did a video on the British Standard Code of Practice. We are able to obtain moment at different sections of a simply supported bridge using the HA and HB load configuration. Whatever code you are using, you can do that, making use of your influence line to obtain the moment at various points. Now, in pre-stress concrete design, you need to obtain moment at various points because it's necessary for you to check this cable zone. Okay, if you don't have the moment at various points along the beam, you can't check this cable zone, because you can see from what I've drawn on the board that this cable zone is varying in its curve. Is going, the value here is different, the value here is different, the value here is different, so it goes on and so on. Okay, so now what I'm trying to say is, if you are designing for your bridge, you pick arbitrary points, close points, that will be convenient enough for you to check this variation of this cable zone. All right. Now, for this cable zone is gotten from plotting of this cable eccentricity. All right. Now, the positive cable zone is from this point of your neutral axis. Let's say these are neutral axis, NA. Above your neutral axis is assumed to be the positive, to give us a positive eccentricity, while below your neutral axis, like we did, is expected to be negative eccentricity. So let's assume here is our 0 point, which is the neutral axis. So you plot this thing, the cable zone. So you can see that we need to have two equations to be able to plot the upper and the lower limits of the cable zone. If this becomes the upper limit of the cable zone, this other curve represents the lower limit of the cable zone. Okay, so once you're able to get this cable zone, so you can shade all these points. We are not interested in this point. All these points are not our interest. The middle, the space between this curve, represent our cable zone. So at every section of your beam, you will observe that the cable zone varies in values. Okay, so the width between this upper and lower boundary is all called the cable zone width. Okay, so having known this, the next thing we want to do is to obtain the equation for determining the cable zone. Like you can see from the board, we have four basic equations for the eccentricity, but which of these equations represent the upper limit of the cable zone, and which of these equations represents the lower limit of the cable zone? This we cannot determine. Let's resolve this equation mathematically using our knowledge of inequality to resolve it, so we can know which equation is suitable for our cable zone. Now, but from when we look at the inequality on the board, if we look at carefully at the inequality of the board, you'll discover that if ES is lesser or equal to this and this, and ES is greater than this, it means that EX represents the upper limit of the cable zone. All right. So this is the maximum eccentricity. The eccentricity shouldn't be more than these values, Okay. Now between these two, which of them represent the upper? Because of course, if you substitute values for this, you discover that this one, equation 3a and equation 3b, will have different value. For example, if you have one that will produce, or whichever that will produce the lower limit of the upper limit, as we can call it the lower bound limit of the upper limit. So that equation that will give you a lesser value, because these two represent the upper limit. So any of them that has highest value represent the upper limit, while the one that has lower value represent the lower bound of the upper limit. Okay. All right. So let's not get it confused. All right. I believe we are flowing. Okay. So let's go with the second. Now we have two equations here. Uh, this equation is eccentricity is greater than this, eccentricity is greater than this. Of course, this greater means this equation represents the lower limit of the cable zone. Now, which of them will give us the very lower limit? So if you do this in a curve, this is what you're going to have. Let's have a curve in a beam. Let's assume this is a cable zone. When you plot this equation, let's assume you have this first cable zone. Maybe you plot again, which is the lower limit. Sorry, this is the lower limit. So you plot again, you have another line. You have another line. So you can see we have 1, 2, 3, 4, 4 cable zones. But which of them represents the upper and the lower limit? Now, take a look at the cable zone. We must ensure that the cable zone satisfy what we call the cover requirement. Because once you have this zone of the cable, you must create room for your concrete cover. So whichever of these cable zone you are picking must not fall outside the beam. The values you're going to plot must not fall outside the beam. So you must ensure that there is a reasonable cover for your prestressing strands or tendons. Okay, so that gives us a guide to that. So what we are going to do now, we are going to establish the cable zone. We have 4 equations. We needed just only 2 of those equations to get the solution for the cable zone, the equation for the cable zone. And we're going to plot that in a graph and get the solution. So when we have these 4 solutions, let's see how we can considering equation inequality, equation 1a and 3a. Okay, so when we consider equation 1a and 3a, we'll have the upper limit to be equation 3a, and the lower limit becomes equation 1a. So we pick it from there. So let's go about that. So we have that Z1 over A minus F maximum minus N1 close bracket Z1 over P close bracket minus M1 over P is less or equal to equation 3. We pick equation 3. Equation 3 is Z1 over A minus F minimum minus N2 Z1 over P close brackets M2 over P. All right. So when we compare equation 1a and 3a, this is what we have. So solving this inequality, we are looking for the moment variation. So we're going to have this as M2 minus M1 over P is less. Now let's pick the like terms. We're going to express this term Z1 over A here. So taking this, we're going to Z1 over A is going to strike Z1 over A. So this is going. So we're going to be left with this. So we're left with minus. If we take it this way, it becomes plus F maximum minus N1 close bracket Z1 over P. Okay, I will have this, which is already a minus sign. We'll have it here minus F minimum minus N2 or bracket Z1 over P. Okay, and that is what we have for this one. Okay, so looking at both sides of the equation, we have P on both sides. So we're going to have our Z1 multiply both sides by multiplying both sides by P. M2 minus M1 less than F maximum minus N1 Z1 minus F minimum minus N2 Z1. Okay, so this is what we have as the moment variation. So let's express it in a much more better way in terms of our fiber stresses. So we'll have M2 minus M1 bracket less than. Okay, so for do that, we're going to have we have Z1 as a factor on both sides. So we can say that this becomes Z1 bracket F maximum. We'll have this minus F minimum. Okay, then we'll have plus N2. This becomes plus N2 minus N1. All right, all into bracket Z1. So if we simplify further, we're going to have this as M2 minus M1 less than, we have Z1. We have, let's assume N2 and N1 becomes 0. So if N2 and N1 becomes 0, we'll have it as Z1 bracket F maximum minus F minimum. Okay, where N2 is equal to 0 and N1 is equal to 0. Okay, so this becomes a final expression where we do not have axial forces present in this structure. So we'll have this as our equation. So this becomes, we can call this our first equation we derive. So the moment variation becomes lesser than Z1 F maximum minus F minimum. Let's call this, we'll call it equation, let's call it equation number 5. All right, equation number 5. So we just solved one of these equations. The next thing we are going to do is to compare the next one. Let's pick, for example, let's pick, we can decide to pick 2a versus 4a. All right, so we pick equation 2a versus equation 4a, and let's get the solution. Now, if we look at this, this is one of the equations. Later, we are going to compare this with the equation of a straight line. But let's derive all the necessary equations. We'll compare them to equation of a straight line. So let's pick equation 2a and 4a. So from equation 2a and 4a, we can say from equation 2a and 4a, let's equate and work it out. Now, equation 2a, of course, the upper limit is equation 4a, while the lower limit of eccentricity is equation 2a. So writing it, the inequality, we are going to have it as F minimum minus N1 into bracket Z1, sorry, into brackets Z2 over P, okay, minus Z2 over A, okay, close bracket M1 over P. Okay, this is lesser than the upper limit of the eccentricity, which is equation number 4a. Becomes F maximum minus N2 Z2 over P. Okay, they will have minus what? Z2 over A, and lastly we have minus M2 over P. So that represents equation number 4. Okay, so it represents equation number 4. So let's solve that and look for the moment variation for that. This represents equation number 4. So let's solve that and get the moment variation in terms of this. So we're looking for M2 minus M1. So we do what we did. Picking up the like terms, we're going to have it as we're going to have M2 minus M1 over P. Okay, M2 minus M1 over P. Then we have less than, let's pick the terms again. We have Z2 over P here. We have Z2 over P. We have Z2 over A. We have Z2 over A. So if we collect like terms, they are going to strike out each other. This minus. So picking up like terms, we have this and this also going. All right. So maximum minus N2 bracket Z2 over P. Okay, then we have minus F minimum minus N1 Z2 over P. Okay, so this is what we have. All right, so expressing it, we have this expression. So like both side by P, we'll have P striking P on both sides of the equation. So we're going to have M2 minus M1 less than, we'll have F maximum minus N2, okay, bracket Z2, okay, minus F minimum minus N1 Z2. All right, so this is what we have now. We have Z2 on both sides, so we can factor it out so that the expression becomes M1 is lesser than Z1 brackets F maximum. Let's pick the stresses, the fiber stresses. F minimum, say F maximum minus F minimum, negative N2. So this becomes plus N1 minus N2. Okay, N1 minus N2. All right, so this is what we have for it. All right, so we can we'll have it as this. So we can decide to give it, remember, yes, Z2, sorry, this is Z2. Okay, this is Z2. So we can have the moment variation M2 minus M1 lesser than, let's assume our normal forces are 0 as usual. So we have the equation as Z2 bracket F maximum minus F minimum bracket. This, we can call this equation number 6. Okay, so we can call that equation number 6. Equation number 6. The next we are going to go is, we have done 1 and 3, we have done 2 and 4. The next we are going to do 1 and 2. Okay, and we'll do 2 and 3. We're going to do equation 2 and equation 3. And once we do equation 2 and 3, we equally do equation 1 and 4. All right, so let's do that. So the next we're going to consider, let's consider equation 2 and 3. All right, so if we consider equation 2 and 3, equation 2a and 3a, the upper limit as equation 3. So we're solving this, we're going to have the expression as, let's go, we have equation 2a as f minimum minus n1, f minimum minus n1, z2 over p, all right, minus z2 over a, all right, minus m1 over p is lesser than, let's go to equation 3. With equation 3, we have z1 over a minus f minimum minus n2, close bracket, minus, close bracket, z1 over p, and we have minus m2 over p. Okay, so this is what we have for equation number 3. M2 minus M1 over P less than Z2 plus Z1 over A. All right, we have minus bracket F minimum minus N2. All right, close bracket, Z1 over P. Then we have it as this, Z1 over P. Then taking this one this way, we're going to have F minimum minus N1, okay, bracket Z2 over P. Okay, so this is what we have as the expression. So we have it as this, M2 minus M1 is less than, okay, we need to have P bracket Z2 plus Z1 over A. All right, and we have here minus, this becomes, let's take the like term. So we have minus F minimum Z1 over P. Let's look on this. This becomes minus F minimum Z2 over P. Okay, now we have this becomes plus N2. All right, this becomes this becomes plus N2. Why this become plus N2? Why this become plus N1? Okay, all bracket. Why N1 is Z1, Z2 over P. We have N2 to be, sorry, let's write it this way. Let's come down this way. So we have plus, we have N2 Z1 over P, and this plus, they'll have plus N1 Z2 over P. Okay, so we have N2 Z1 over P, we have N1 Z2 over P. So this gives us the expression, because this negative positive, this positive, so we have it as this. Okay, so it further, and let's go over to the other side of the board as we simplify it further. We'll have N2 Z1 plus N1 Z2. Okay, comes our equation number 7. P brackets Z1 plus Z2 over A F minimum Z1 plus Z2. This becomes our equation number. All right. So this becomes equation number 7. Of course, we are going to have 3 basic equations of inequality. So we're going to have the next one, which is the next equation. So in this case, we're going to be comparing equation equation 1a versus a versus equation 4a. Now let's start a minus f maximum minus n1 z1 over p minus m1 over p less or equal to equation number n2, okay, z2 over p, we have it as minus z2 over a, or minus m2 over p, okay. So this what we have as the expression. So solving this equation 1a and equation 4a, we'll have bringing the moment variation, we have it as m2 minus m1 is lesser, m2 over m1 over p is lesser, as z2 over a. All right, we'll have this as a negative value. So now in terms of the fiber stresses, we'll pick it. We'll have maximum and maximum, so we'll pick it, and we'll have this is a negative one. I'll have this as positive, so if it moves it become positive, so I'm going to have positive fiber stress. So maximum bracket, this multiplied by this will give you z2 over p, this multiplied by this will give us plus z1 over p. So this is what we have for the fiber stresses. Okay, so we've gotten this section. Now let's take in terms of the axial stress, axial stresses n1 and n2. So for n1, this way, if we take it, it become n1, this negative, positive, so it become negative n1 z1 over p on this side, and we'll have also negative n2 z2 over what? Over p. Okay, so this is what we have as the expression. So if we do this, so this side multiplied by p, it gives us negative brackets. This becomes z1 plus z2. P cancel p, so the p strikes it out. So we'll have this going. We'll have m2 minus m1 lesser or equal to f maximum z1 plus z2. Okay, this gives us of course we know that n1 and n2 is assumed to be 0 in the case of a beam, when the structure is analyzed as a beam, so we assume that one to be 0. Okay, so we have this as the expression. So this becomes our equation number we can have equation 8. So let's call this equation 8. Okay, so we have this as our equation number 8. So with these 4 equations we've just derived, we can determine the prestressing force, which is the solution to this equation. But first of all, we're going to put it in a graphical form, and we know that we can easily obtain the equation of the graph. Of course, when both lines intersect, it gives us the solution to P. So we're looking for the prestressing force. And let's go over and see the prestressing force in this. So this, we have this four equation. Equation number 5, equation number 6, equation number 7, and equation number 8. So with this four equation, we're going to plot a graph showing these equations. All right. We'll be able to determine the solution of the equations, the four equation 1a to 4a. We're going to have their solution, the solution for P, and also the upper and lower limit of the prestressing force based on these four equations which we have just gotten. All right. So equation 5 to equation 8. Okay. So let's do it graphically. I will solve equation 5 to 8. What we're going to do is to draw the graph of equation 5 to 8. But before we do that, let's rewrite the equation from equation 5 to 8. Let's start with equation 5. We have equation 5 as m2, m1 is less than z1 bracket. We have f maximum minus f minimum. This is equation number 5. Now we have equation 6. Equation 6 is we have equation 6. Equation 6 is m2 minus m1 is lesser than, where is it? Equation 6, z2. We have that as our equation number 6. All right. Then we have equation 7. Equation 7 is, we'll have it on the other side. We'll have it as m2 minus m1 less or equal to p bracket z1 plus z2 minus f minimum bracket z1 plus z2. This is equation number 7. All right. I've gotten equation 7. The next we're going to do equation 8. We'll have equation 8 as we'll have it as m2 minus m1 is lesser than f maximum. All right. F maximum bracket z1 plus z2. All right. Minus p bracket z1 plus z2 all over what? A. This equation number 8. All right. So I haven't gotten this equation. The next thing we are going to do, we compare it with the equation of a straight line. If we compare it with the equation of a straight line, remember that the equation of a straight line is y is equals to mx plus c.